Welcome and thanks for the opportunity to be here in this virtual meeting. I'm Felix Schöfer of Quart in Zorneding. I've put a picture of myself here as you can't see me, used from a real life meeting. Quart has been present in QA since about 45 years and internationally present since about 20. We do all sorts of X-ray QA, dosimetry, and software and specimens phantoms. Today I want to talk about QA solutions for cone beam and computed tomography. I have decided to show two of our QA systems, now starting with the first one. The first one is a test system for all kinds of CT systems, cone beam CTs, dental cone beam CTs, all scanners you may think of. We use it for the CT Tech software and Phantom. The Phantom itself has been present for quite a while. It has been established with a German standard for dental cone beam CT about 8 years ago, and has been present and internationally present since the standard was translated by us. Additionally, there's a draft of an IEC standard for dental cone beam CT that adopts the same Phantom, and we have had different collaborations where it was used on other kinds of devices. The software we use to evaluate data sets taken with this Phantom is our CT Tech software. The database structure is as follows. Starting from the upper left corner, you can edit or enter multiple users. For each user going clockwise, you can add X-ray devices, as many as they have, and for each X-ray devices tests below, and tests of dose and tests of imaging quality. The lower left corner is used to show information connected to wherever your mouse is on the display. In order to connect the data we acquire to a dose measurement, there's two ways of entering a dose into the software. One is a standard CTDI measurement, and this one is the dose measurement we suggest for cone beam CT applications and also adopted in the DIN standard. You mainly measure the dose on the detector, and the geometric data helps to calculate it to a value of dose at the isocenter, which is equal for a cone beam CT measurement to the CTDI free air measured in the center. The dose meter is of course to be specified in the software for later reporting. Now we can turn to the imaging performance. We have to prepare slices from the dataset acquired with the Phantom. We have to get the test Phantom used specified for the report, and we have to get through a checklist of tests that we should do to be sure that the system is in good shape before we start. The evaluation of the data we just prepared is done in 3 steps or 3 views of the software. On the very left side, you see the test that you are performing. The main part shows the data set and the part of the data that is evaluated. And on the right, you find a short description on what you should do and the results. Going through the tests on the left-hand side will result in going down in the list on the right-hand side and replacing all these question marks with results, and of course always being informed about how to do the test. There are further possibilities to get everything automated by pre-setting the ROIs and just checking if the software goes through it the same way it always does. Here we have a close-up of the dataset showing the structure that is evaluated for the Nyquist frequency, the MTF edge that is between the ring of PVC and air on the left-hand side, and the CNR, which is defined on the contrast between PMMA and PVC. The example for the guidance in the middle is for the modulation transfer behavior, and if the ROI setting is in some way wrong or not done yet, you get shown on how to do it. When you put it on the right place, you will get a result like the one on the right side, showing the MTF and the calculated MTF 10% and MTF 50%. The calculation method standard is adopted from the mammography standard. We have two others. One is from the dental standard, or DIN, which is a simplified way of finding an MTF, and a self-developed pre-sampling MTF that we also included in our software. When we are done with all the testing, the tests performed will be the ones on the left-hand side. We have from top left Nyquist frequency, contrast noise ratio below, homogeneity, MTF measurement, the CT numbers of air, PMMA, PVC, and also water, and the Nyquist frequency in Z direction of a sagittal slice, contrast noise ratio same direction, and MTF in that direction. Then we of course can see all these results in a table. We can export this data into Excel, and on the next page I will show you a full report. There's a pre-designed report included in the software that can be left with the device tested for reference. It includes all the used devices and who did do the testing, and the main points of the tests. On the back side shows the MTFs of the system. Here you can see the 50% MTF and the 10% modulation transfer function. The later one is not reached by the MTF graph, so set equal to the Nyquist frequency. There is additional software available for constancy tests in dental DVT according to the German standard, and adaptations to other national standards will be done shortly when the IEC standard is published. Here in Germany, we have to do the constancy tests every month, so it results in a table of monthly tests. For our customers in the dental field, we have software supporting the acceptance tests. Usually technicians come in, have multiple users. Each user may have multiple X-ray devices, and for each device, the acceptance tests are regularly performed. So we have a database structure following this on the left side here, and on the right side you see the data that you already chose. So if you start from top, the user data, the device data, and the acceptance test afterwards. That was it for the software and phantom of our cone beam applications. If you have any questions left or rising on this, please contact me as soon as possible because I'm looking forward to it. With this, I want to turn to our Nonius device. It consists of a measurement system, seen on the left, and software, seen in the background on the right, and used for collimation tests, which are interesting on cone beam devices to find field edges on a detector, even if you don't see single radiographs during the acquisition of the volume, or you want to see on a CT system the moving of the fan beam or cone beam about the patient. The Nonius device has a linear array of detectors that can be positioned either in a radiation field or fan beam region or on the edge of a fan beam. There are various markings on the cover to allow for correct positioning. This is the Nonius software. It has a small database behind to collect user and device data. Here you see the main measurement screen. The positions can be chosen in the lower left corner. In the graphic you see one of the measurements chosen. Here a series of measurements of a CT fan beam moving about the detector array. After this you see the definition of the field edges as a ratio to the max found on the array can be chosen between 0 and 100%, and the collected results for edge measurements of one or two edges producing a fan that has a center and a width. Here you see on the top left side the series of measurements where I show to you just a single one. It tends to be a bit confusing, but it is the moving fan from right to left of the CT scanner. On the right hand side you see the result when I position the Nonius device in the isocenter of a rotating fan beam. There you see the center doesn't change, changes about the blue part of the graphics, and the width changes a bit as the fan hits the array from the side. With this, I come to the end of my talk. Here you find my contact data again if there are any questions left, or even better if you have new ones on these QA solutions for cone beam and computed tomography, or any other QA of X-ray systems you may want to check. Thank you very much.